Alright, so begins part 2 of lecture 7. So we've so far talked about the covariant derivative, how to calculate it, basically with respect to the Cartesian frame. Now we're going to up the ante and talk about just more arbitrary frames. They could have a point dependence, right? So let's let E1, E2, E3 be a frame for R3, and let's let V be a vector field. We can find, there exist functions, let's say f upper j, which if you like we could define by v dot ej, alright, such that what? Well, we can express v as a sum of, say, f1 times e1 plus f2 times e2 plus f3 times e3. These are the component functions with respect to the frame. Or I could call it the e-frame, since I have no better idea. Well, if you calculate the covariant derivative, right, of v with respect to w, it's interesting to see how that works out in terms of this frame. So what do we got? We've got the covariant derivative. This is exciting. We're going to get a chance to take all these new identities we have for the covariant derivative out for a spin. Let's see here. Fi, ei, so I just expanded v in its frame expansion. But you know what? I can also find component functions for w. So I'll call those g, gj, ej, so that's, if you're wondering, gj is defined to be w dot ej. That's the jth component function of w with respect to the e-frame. Great. Now I use properties of the covariant derivative. Alright, so first of all, we can pull out the sum over I, and we can pull out the f upper I, because we have that kind of linearity in the slot, which shall remain nameless. Okay, ei, there we go. And great. And I guess I could have also pulled out the sum over j, so let me just go ahead and do that, comma j. Alright. But what am I left with? Well, I've still got gj, ej in here, right? And that's a product of two things, neither of which may be constant. So I need a product rule here. Of course, that product rule is provided to us in the previous proposition. We got a sum over I and j of fi, parentheses. Let's see here, how'd that go? That was going to be let's see how'd it go. It was ei acting on gj, alright, ej, plus gj, covariant derivative with respect to ei of ej. Alright. So we can call these, I can write these out again. So what I really have is a sum over j. So if you look at fi ei, that's just v. So this is really just v acting on gj, ej, plus a sum over I and j of fi gj, covariant derivative in the ei direction of ej. Now if you look at it, if I call this 1 and 2, right, you'll hopefully recognize that we had 1 before. 1 is exactly what we had in the Cartesian frame, with gj being w upper j and ej being u sub j, right? But this was not there before. This is something new. Alright? And it's not surprising this wasn't there, because, of course, if you take the covariant derivative of the Cartesian frame in the ith direction, in the jth direction with respect to the ith direction, well, it's constant, so it's 0, right? So this thing vanishes in the Cartesian case. But more generally, we're going to define this piece in terms of what's called the connection form. Now the fact that it's a form is really given to us by that linearity I was pointing out in part 1 of this lecture. Of course, form has to be pointwise a covector, and that is the case for this. So here's the connection form, and it's the connection form really of the E-frame. All right, and so what it is, we have omega ij of the, what is that equal to? Well, that's equal to the covariant derivative in the v direction of ei dot ej. All right, and at the point P, of course. And I guess if I wanted to be really pedantic, I would say this is also at the point P. And that's for each V in TP. R3, we have this, right? Then, of course, the assignment I guess I was, I guess to be really annoying, I should probably put a of P here somewhere too. Oh well. There, that's annoying. I don't know. Don't make too much of this notation. The assignment anyway of P to omega ij of P, right? I guess I should probably put the P here and so I can put the V out here. Feel better about it. All right. Whatever. The assignment P goes to Wij of P is a differential one form. All right. On R3. Okay. So there you go. That's the connection form. Now I would point out already, we already know something about the connection form from one of our previous examples, right? So I would say the observation we can make immediately. Right? Omega ij is equal to minus omega ji. How do I know this? Well, let's look back at page 4. All right. Here it was. So let's see here. What is this? This is basically omega ij of v, and this in retrospect is minus omega ji of v, but it holds for all v. So we can just say omega ij is equal to minus omega ji. Cool. So in principle, you might worry that you had 9 of these guys, because I and j are, they go from 1 to 3. But once we have this, well, it's an anti-symmetric. That means that omega ii has to be equal to minus omega ii, which is just a fancy way of saying it's 0. So this basically immediately tells me that there are just 3 independent connection forms. For R3, because that's the number of components you need for a 3x3 anti-symmetric matrix. Matrix, you say? Yes, matrix. All right. So that was half of the proposition I'm about to state here. 5. This is 6. So the proposition is what? I guess we're just really recording what what I just explained, omega ij is equal to minus omega ji for a connection form. And, by the way, the covariant derivative you can build from the connection form as follows. The covariant derivative of EI in the v direction is equal to a sum j equals 1 to 3 omega ij of v ej. So I guess that means the connection form is really telling you how the EI vector field changes in the v direction. In particular, omega ij of v tells you how I rotates into the j direction. But there's also this v. I'm going to put that into words exactly. All right. Actually, this is actually immediate from the calculation I had on the previous page. There. So if you just go back over here, right, input W equal to EI. If W is equal to EI, that means that the GJ is just 1 or 0, and so this term vanishes and you're just left with this. But again, the GJ quote unquote is just basically for a fixed I. It's for fixed I. It's Kronecker delta ij, really what it is. And fine. Proof. So let W equal to EI. All right. That says what? If W is also equal to some or GJ, EJ, just trying to, then what's that mean? That means that by comparison, G upper J is equal to Kronecker delta Ji. And so if I go back to that calculation again, we have covariant derivative of V, W is EI, okay. It's equal to 1 plus 2. Again, the 1 is 0. I'm not going to write it. Right? This term is 0 because GI is just a constant. But we're left with, I'll write this out, sum ij, find f upper I, Kronecker delta, Ji, excuse me, covariant derivative of Ej with respect to, oh no, I think I have misused I. Oh, let's make this an L. This I is fixed, right? I can't use a summation I to be, that confuses the meaning of I. So let's make it an L. 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 Fine. EJ. Let's see, where was I? So. Kronecker delta Ji. So we'll keep the sum over L. And that gives us covariant derivative EL. Let's see here. Now J is now equal to I. Oh, great. So if I bring this inside, I get the covariant derivative of V. Yeah, okay, very good. The circle is complete. All right, fine. So I think there's only one thing to do to this proof at this point. All right, let's take another look at it. We have omega I j. I'm going to drop the point dependence, if you don't mind, of V is equal to the covariant derivative of the EI dot EJ. Okay, so what does this mean? This means that the jth E-frame component, right, of the vector field, covariant derivative of EI within the V direction, is just, which we could, well, I don't really want to denote it by upper J because that's reserved for the Cartesian frame, right? Fine. Is omega ij of V. So therefore, by our general work on orthonormal frames, that stands to reason then that this is equal to a sum j equals 1 to 3 of omega ij acting on V ej. Just simple as that. It's just an orthonormal frame result. Duh. Duh, 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 duh. So sorry. Sad, 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 sad. All right. So that brings us to talking about matrices of differential forms. I'm going to stop and get a drink, and I'll be back.